So again, it's important to revise what are these different types of points for the box constraints. So if you have an equal to 0, then the points are inside the margin and they are correctly classified. If they are greater than 0 but less than c, and but your xi variable is 0, then they are on the margin. If an is equal to c, all right, and but xi is less than equal to 1, then they are correctly classified, but they are across the margin, and then these are the points that are incorrectly classified. Okay, so to give you to write it more concretely, so let's say this is your these are your axes, and this is your decision boundary, and this is the margin, and let's say this is the positive side, this is the negative side. Let's just talk about positive points. For positive points, here an is equal to 0. These are these points. The points on the boundary are these points for which an is not 0. It is greater than 0, but it is not c yet. It has not become c yet. Okay. And xi is still 0. Slack variable is still 0. Anything on this side, xi is going to be, anything across the margin, xi is going to be greater than 0. Okay. Up to the boundary, xi is going to be less than equal to 1. After the boundary, it is going to be greater than 1. Alright. And any point that intrudes into this space or gets misclassified, for that an is going to be exactly c. Now the good thing about this formulation is that every point that intrudes into the margin or goes across the margin, its influence does not increase. Its influence always remains c. Okay, it is capped by c. So that is the box constraint. So what this means is that there is some sort of natural tolerance for outlier points. So if a point becomes noisy and it is like somewhere very far away from the boundary, its influence on the boundary is same as any point that has intruded into the margin. It doesn't matter how far it has intruded. So that is capped at c. And this c can be the hyperparameter that we tune. Okay, and you will see that there are other ways of formulating the hyperparameter, the trade-off hyperparameter. Okay, that will tell you about the trade-off between number of support vectors and the smoothness of the boundaries in the X space. So here I have just drawn a linear boundary because I have not used the kernel, but ultimately what you will have is a kernel also. So what you will actually have in the X1, X2 space, okay, let's say you have a bunch of positive points and then you have a bunch of negative points, right? So some of these, how many of these points, so let's say there are some points that are misclassified, right? There are some points that are noisy. Let's go back here. So let's say there is a negative point here, there's a positive point here. Okay, these points came because of some mistakes, right? Now, do we want a boundary that basically goes like this? Okay, if you want a complicated boundary like this, then we need a lot of support vectors, right? Those support vectors are going to be like this one, basically the points that seem to be close to the boundary. So if you are assuming a Gaussian kernel, these might be the support vectors, right? So it's a very complicated boundary, and it is not tolerant to this noise that we saw in these 2 points. Instead, if we want to right, so like a boundary like this, right? So this is not a noise tolerant boundary. On the other hand, if I draw, let's say, similar type of points in and use a smoother boundary, and let's say this is misclassified and this is misclassified, right? A smoother boundary might look like the following, just this, right? So if we just have a smoother boundary like that, we will have fewer support vectors, Okay, and perhaps this is going to be a support vector, this is going to be a support vector, because anyway it's far from the boundary but it is misclassified. So for this an is going to be greater than 0, but it will not exceed c, and let's say perhaps just a few number of support vectors, and I will get a noise tolerant boundary which is smoother and that has a more regularization effect on the classifier. Okay, so that is how the kernels the trade-off between how many support vectors you have works when you change C. Okay. Now in many of these kernels there is a second hyperparameter, right? So C is one hyperparameter. Okay, so which are the hyperparameters? One is the C itself, that is common to everyone. But now for kernel specific hyperparameter can be, for example, the sigma or the kappa that we had for the Gaussian kernel, or the degree that we had for the polynomial kernel. Okay, so those are going to be kernel specific hyperparameters, and the best classifier that you can find is that gives you you will try different values of hyperparameters using some sort of a grid search. So you will have, let's say, C, and you will have kappa. Okay, and you will have certain values of C, 0.1, 1, 10, right? So 3 different values of C, 3 different values of kappa, 0.1, 1 and 10, and so you have 9 different combinations to try, and you will try these 9 combinations on validation data, the one that gives you best results on the validation data. So let's say this one gives you the best result on the validation data. That combination is what you're going to use on the test data. So that validation and hyperparameter tuning using grid search, those ideas that we learned in machine learning for smart monkeys or linear classification, those are also valid here. So again, let's revise what points define the boundary. Those points where xi equal to 0 are on the margin, right? And but an will be greater than 0 for these points. They can be between 0 and 1. Xi n can be between 0 and 1, or it can be greater than 1. So xi n is equal to 0 for points on the margin as well as points that do not matter, the non-support vectors. Okay, so the computation of yn will remain the same as we saw for the hard SVM. Okay. Now let's look at the last topic for support vector machines, and that is support vector regression. Now this is a slightly mind-bending idea, so look at it a little bit more carefully. We'll start with the linear concepts and then we will go into kernels. Okay, so let's first start with the classification problem. In classification problem, let's say you have an x1, x2 space, and our objective is to find a boundary, okay, such that all the positive points are on one side, all the negative points are on other side, and they do not intrude into the margin. So all the positive points are here, some of them are on the boundary, all the negative points are here, some of them are on the boundary. So these are the support vectors, they are on the margin. So this is classification, support vector machine classification. On the other hand, what we have for regression is we have, let's say, y and x, right? So this is x, this is y, or t, what we want to predict, right? Here we want to find a line, right, such that there's a margin around the line, okay, and all the points, there's no positive point or negative point, all the points are inside the margin. All the points are inside the margin. They are almost as if there's a band around the line and they are roughly following the line. The points that are on the margin, okay, these are the support vectors, right? So there is no point outside the margin. it's a regression problem. So this is a regression problem. Okay, so we have now two slack variables. So here we could fold this space, right? We could fold the negative space onto the positive space. We could use this as a mirror or a fold in a paper, and we could fold it over by multiplying with Ti. So Ti is -1 on one side and +1 on the other side. If we multiply W transpose Xi plus B with Ti, we are folding it on the boundary so that everything is now positive when multiplied by Ti. Right? So we don't have that advantage in regression. We have points that can go outside the margin above a line, or below the line they can go outside the margin. So we now need two slack variables, one for above the line and one for below the line. Okay. So your error. So basically we are going to have a noise tolerant. Let's go to the next slide. So what we are going to say is that our loss is such, right, that, so this is your loss. Okay. And what is the loss? Loss is going to be on this Ti minus Yxi. So our loss is going to be tolerant. There will be no loss as long as we are inside the margin, but outside the margin there's going to be a loss. Okay. So up to plus epsilon and minus epsilon, between minus epsilon to plus epsilon, we have no loss. These are all the points that are close to the line. Okay, so this is for regression. And by comparison for classification, our loss was like this. Okay. So it's similar, but except that we have a small noise tolerant region where it does not matter if the point lies. Points that lie on the boundary here, or here, those are the support vectors. Those that lie inside are not the support vectors, and nothing lies outside. Or we can even formulate it as a soft margin regression where some points are allowed to lie outside. I will not go into soft margin regression. It's just a straightforward extension of soft margin classification. Let's just look at the hard margin regression, and then we will leave it at that. The dual form can also be derived very easily from that. Okay. So here we will have the mean square error. So if we have regular regression, we will have mean square error, right? So mean square error is going to be half of sum over I, okay, yi minus ti whole square, okay, plus some regularization term mod of w square. So this is mean square error for linear regression. Instead, for support vector regression, the loss is going to be that we will have some c times I, okay, yi minus ti, sorry, we will have this expression, the loss E epsilon, okay, of yi minus ti. What is E epsilon? This is precisely E epsilon. This red curve is E epsilon, okay, of yi minus ti. So I will just call it yi minus ti. Yi minus ti. Okay. So E epsilon of yi minus ti plus half mod of w square. Okay. So these are two different ways. The first one is not for support vector. The second one is for support vector regression. The first one is for regular linear regression that is solved using mean square error. Right. So here this E epsilon is nothing but the red curve that is drawn above. So here your E epsilon of yi minus ti is equal to max of 0 comma yi minus ti mod minus epsilon. Okay. All right. So now we have two slack variables. Okay, one will be xi, the other will be xi hat. Let's say it will be xi hat. So basically what you will have is ti is less than equal to yi plus epsilon, okay, plus the first slack variable xi, and we will have ti will be greater than equal to yi minus epsilon minus xi hat of I. This is the second slack variable. Okay, and basically your objective can change to C of sum over I xi I plus xi hat of I, okay, plus half of mod w square. So see the difference between C and lambda is that they are just inversely related to each other. You can, what C does, that's the same thing as what 1 by lambda does. What lambda does is the same thing as what 1 by C does. So it's they are just equivalent. It's just a matter of preference that whether we put the hyperparameter as C or as lambda. They are just equivalent, just reciprocal of each other. Now here the xi and the xi hat is basically saying that this particular loss function is made up of this curve and it is made up of this curve. So let me remove that. So basically it is made up of this curve plus this curve, right? So these two curves are, one of them is the xi, the other is xi hat, right? And they are both greater than equal to 0, and they're defined in to find points that go above the margin or below the margin of that regression line. Now it is regression, right? Not classification. So this same analysis we can converting it into a dual form that we did, we can do that dual form for epsilon for regression also, and based on that we will get everything in terms of dot products, and then we can replace that dot product with a kernel, and we can get non-linear regression for support vector machines. So I will leave that perhaps as an exercise in one of the tutorial sheets for you to look at. All right, thank you.